Hi everyone. In this video, we will finally define the Lebesgue integral. We will begin first by defining the Lebesgue integral for simple functions before later in another video moving on to the Lebesgue integral of a general measurable function. So we want to begin by thinking about our motivation for defining the Lebesgue integral and what properties we might want such an integral to have. So we want to think of the Lebesgue integral as something analogous to, but broader than, the Riemann integral. So there are two key properties of the Riemann integral that we probably wish for the Lebesgue integral to preserve. So the first is we would like the Lebesgue integral to have this characteristic function property. So the idea here is if I take the Lebesgue integral of the characteristic function of an interval, that ought to give me back the length of the interval. Now, one way to think of this is analogous to saying if I take the Riemann integral of the function 1 on the interval AB, right? I just get B minus A. Or equivalently, you could just think of this even as the Riemann integral from minus infinity to infinity of the indicator function of the interval AB, right? But either way, this recovers the length of an interval. So again, we want this to certainly be the case, okay? And the second thing, we certainly want any sort of integral operation we come up with to be linear, right? So I'd like to be able to break it up over sums, and I'd like to be able to pull out constants, right? So however I define this integral, I would like the integral of r times f plus s times g to be r times the integral of f plus s times the integral of g. Again, this is also a property the Riemann integral has. These are key properties of the Riemann integral that we would also like to see hold for the Lebesgue integral. All right. So in thinking about the Lebesgue integral, when we think about it, particularly this property, we recognize that this in some ways is saying how an integral handles something about length. Okay, and so we actually want an analogous property here for the Lebesgue integral to be that the integral of the characteristic function of a measurable set E ought to be equal to the measure of E. So if you notice here, this is just talking about intervals, but we'd probably also like this to be true just for measurable sets. Again, if the Lebesgue measure is generalizing length in a particular way, right, then this ought to also be true. Now notice if you could prove this, then this would automatically follow, right? So again, just as we're thinking about sort of properties this Lebesgue integral should have, this is certainly one we would like to be true. And this immediately makes me think, like if I'm looking at characteristic functions, like this sort of makes me think about, have characteristic functions here, and I have sort of this linearity property here. Well, what is something that is a linear combination of characteristic functions? Those are simple functions, right? So I probably first should define the Lebesgue integral for simple functions. Then, as we saw at the end of the previous video, every measurable function can be thought of as a pointwise almost everywhere limit of simple functions. So if I could understand the Lebesgue integral of a simple function, then maybe somehow I can recover the Lebesgue integral later of a measurable function by looking at what happens to the limits of integrals of simple functions that are converging pointwise almost everywhere to the measurable function in question. So again, we're going to start today in this video just with simple functions. But again, we sort of have some navigational beacons in a way laid out in front of us for how this might help us eventually talk about the Lebesgue integral of a measurable function. All right, so we want to define the Lebesgue integral of a simple function. So let psi be a simple function that is zero outside a set of finite measure. And we're going to represent psi as, again, this linear combination of characteristic functions, okay? And this is well, we're going to call this the canonical representation of psi, where we call this the canonical representation because these sets AK are defined to be the preimage of the value little a sub k. So before we even get to defining the Lebesgue integral piece here, let's take a moment to understand what this is telling us. If I just take any simple function, right, I could have, so take, for example, let me sketch an example here. So maybe, I have some different intervals here, and maybe my simple function even is just a step function. It need not be overly complicated. And in particular, let me draw it like this. Now, one way, so let's say that this is height A1, and this is height A2, okay? So one way I could represent this is I could represent this as A1, and let's give these some names, A, B, C, and D. So I could represent this function psi of x as A1 times the characteristic function of the interval AB, okay, plus A2 times the characteristic function, sorry, I need to of x there, times the characteristic function of the closed interval BC, plus again, A1, where really this I guess maybe this would be A3, but A3 is really equal to A1 times the characteristic function of CD of x. Okay. Now, this is not the canonical representation. The canonical representation, we're saying here that our sets that we're putting, the sets that we're taking the characteristic functions of, the set AK has to be the preimage of A1. So this says I actually have to express this as A1 times everything that maps to A1. So I could write this as the characteristic function of AB union CD of x plus A2 times the characteristic function of BC of x. So the idea here is this canonical representation gives me a unique way of representing a simple function, right? If I don't sort of require this canonical representation, then there could be multiple ways of representing these functions, right? Because you don't know, maybe I split these up. Maybe even I came in here and added some other point D, or some, I guess it would be E in here. And so then I could have A1 times the characteristic function of AE plus A1 times the characteristic function of EB, right? There are infinitely many ways I could express this, right? But if I require this canonical representation, this gives me a uniqueness of the representation, right? It also gives me sort of the most compact way. It sort of guarantees me I'm going to use the number of terms that I have here in this sum will be precisely equal to the number of values in the range. And remember, one of the requirements to be a simple function is that you have a finite range. So again, this avoids all sorts of things like, what if you did some weird thing here and ended up making this an infinite sum? Like, we don't want to deal with that, so we just require we have this canonical representation. In a lot of ways, you could say, just write it in the way that probably makes the most sense. But again, this is mathematics, and we like to specify the exact rules we're playing by. All right, so we have a simple function. It is expressed in this canonical representation. Then we can say that the Lebesgue integral of that simple function psi is, and so this is just how we denote a Lebesgue integral. Notice it looks like a Riemann integral. The only difference is here we have d mu. So this indicates here that we are integrating with respect to the Lebesgue measure. Okay, so this is the Lebesgue integral of psi is equal to the sum k equals 1 up to n of ak times the Lebesgue measure of the set capital AK. So again, notice what we're doing here, right? We're really in exactly the same way. So for a Riemann integral, if you have a step function, okay, so for a step function, right, you can write the step function, say phi of x, as a sum, uh, a sum k equals 1 to n of ak times the characteristic function of an interval, right? And so let's just call that x sub, or let's just call those ik. That's what we did earlier. Okay. And in that case, right, the Riemann integral of phi of x dx could just be expressed as what? Well, the rectangles in the integral, right, they have length of ik as their base and height ak. So you get a sum k equals 1 up to n of the height, which is ak, times the length of that interval. Well, now we're saying for a simple function, psi of x, we can write that as a sum k equals 1 up to n of ak times chi of ak of x. Now, keep in mind here, we are making no assumption about this set capital AK other than it's the preimage of this and it's measurable. Okay, so AK is not necessarily an interval. We can't take its length. What we're doing here is we're saying, well, if we're going to define this Lebesgue measure, then it really ought to sort of do the same thing the Riemann integral does. It ought to take heights times the lengths of bases, but now these aren't intervals. So I can't talk about length, but I can talk about the measure. So again, in a way, it's very much like generalizing a Riemann sum, and you're just replacing length with measure here. Okay. Now, I want you to notice that one immediate consequence of this is that there are functions that are Lebesgue measurable, or sorry, that are Lebesgue integrable, that are not Riemann integrable. Okay. So for example, if I just look at, say, the indicator function of the rationals intersect 0, 1. So notice that I do have this condition that it needs to be a simple function that is 0 outside a set of finite measure. So this is 0 outside of 0, 1, and 0, 1 has finite measure. Okay. This function is not, we've looked at this function before, it is not Riemann integrable. So this is not Riemann integrable. However, it is a simple function, right? Can't spell however, apparently. But however, it is simple, and hence Lebesgue integrable. Okay. Now, the next question we could ask is, okay, if it's Lebesgue integrable, what is the actual value of its integral? Well, the integral of the characteristic function of Q intersect 0, 1 d mu. Well, there are only two values in the range of this function, 0 and 1. Okay, so it ought to be 0 times the measure of this set where this has value 0. Okay, well, this has value 0 wherever on the complement of this. Q intersect 0, 1, or Q complement intersect 0, 1. So it doesn't matter. That term is going to be 0 plus 1 times the measure of Q intersect 0, 1. But remember, this set has measure 0. So you actually get that the Lebesgue integral of the characteristic function of the rationals in 0, 1 is 0. But it is Lebesgue integrable. It was not Riemann integrable. Okay, so we've already sort of made an advance here. All right. Now, what we want to do is we want to prove some facts about the Lebesgue integral of simple functions. And you might sort of feel like, man, we're putting in a lot of work to understand these simple functions. We will then define the Lebesgue integral of a measurable function in terms of Lebesgue integrals of simple functions, and therefore we'll be able to easily pull a lot of those properties over to the Lebesgue integral of measurable functions. So we're starting with simple functions because, no pun intended, they're simpler to deal with. All right. The one other piece of this definition I do want to add on, we can actually talk about, so on the previous slide, we talked here just about the Lebesgue integral of a function, but you might also want to talk about the Lebesgue integral of a function which could be defined on a very large set. You might want to talk about the integral over some subset. So if E is a measurable set, then the Lebesgue integral of psi over E is just defined to be the Lebesgue integral of psi times the characteristic function of E. And another way of expressing this is you take the value of the function, but instead of multiplying it by the full AK, you intersect that with E. So you figure out where on E does the function psi take on this value AK, right? Not where does it take it on everywhere, right? So I could have a function, let's say, defined on a whole interval AB, but maybe I only want to integrate it over the rationals in AB, for example, right? So I can now integrate over sets that aren't intervals, right? So I could take the Lebesgue integral of this function psi over the rationals in the interval AB. Even when the function may be defined on the whole interval AB, I can just take the integral over the rationals in AB. A little thing you can see if you could go as an aside and prove. If your function is Lebesgue integrable, so the Lebesgue integral exists, and you integrate it over all of the rationals in the set that your simple function is non-zero on, then that integral will always be 0. So there's a little thing you could try to prove, play around with some of these definitions and some of our previous facts about Lebesgue measure. All right. Now, the first sort of problem I run into actually goes back to what we were just talking about, which is there are a lot of ways to represent simple functions, right? They're not all in this canonical form. What I would really probably like to show is that that's okay, right? So the first theorem I want to prove is this independence of representation. The idea is, imagine I have my function psi of x, and it's defined to be ak times the characteristic function of ek, where each ek has finite measure, and the sets ek are pairwise disjoint. Okay. Now, I'm not requiring here, right? In the canonical representation, I would require ek to be the entire inverse image of ak. Okay. Here, I'm not requiring that, right? The AKs could be repeated. Okay. These sets, right? I could have E1 and E2, and on E1 and E2, they're distinct. They're sets of finite measure. They're disjoint, but they take on the same value on that interval. Okay. What it says is, well, you can still calculate the integral in almost exactly the same way. So essentially, it doesn't matter how you represent the simple function. We define it, We define the Lebesgue integral of a simple function using the canonical representation, but the value doesn't change if you use some other representation. This is not, we could do everything without proving this. It would just be really annoying. We'd actually sort of have to, I say we can do it without proving this. We would almost have to reprove this every time in a lot of different theorems, because we would need to know that it was independent of this. We'd chosen this other representation. We need to show we actually get the same value of the Lebesgue integral as if we had chosen the canonical representation. So let's first prove this theorem. So let R be some value in the range of psi. And remember, there are only finitely many things in the range of this function psi. Okay. Then the preimage of R. So if I look at all the things that map to R, right, I can express these as the union over all of the AKs that are equal to R of EK. So the idea is I could express the preimage of R as in this other representation. I just go over EK and I say, okay, on which of these sets does it actually take the value R? So maybe there are 3 different AKs that are actually equal to R. So that means there are 3 different sets, EK, that on which the function takes the value R. If I union all of those together, right, then I would get back the preimage of R under psi. Okay. All right. Since these EKs are pairwise disjoint, and measurable, we can use the additivity of the Lebesgue measure to get that the Lebesgue measure of the preimage of R is equal to the sum over all AK equal to R of the measures of the EKs. All right. So this works for every R in my range. Okay. So if I look then at the Lebesgue integral of psi, right? The definition is that I need to take the sum over, in this case, I'm going to just write all R's in the range of psi. Okay. So this is overall AKs, essentially, of R times the measure of the preimage of R. So this is using the canonical representation that these sets, these AKs are the preimage of the range values. Okay. All I'm doing here is I'm writing out explicitly what that is. Okay. So by definition, the Lebesgue integral is defined in terms of the canonical representation. However, I know that for each of these, I can express them in this way. So this is the sum over all R in the range of psi of R times, now this can be replaced with this sum, all AK equal to R of mu EK. But now if I look at this, so for a fixed R, right? If I push this inside, then this just becomes the AK, right? So if I push this inside, then this is just the particular AK. I can re-express this as the sum K equals 1 up to N of AK times the measure of the EKs, right? Because the R value is just the particular AK on that set, right? So I can just push that in and then I recover this sum, okay? I don't have to worry anything about convergence or rearrangement of sums because these are all finite sums, right? So rearranging them is a fairly straightforward process. And so what I get is exactly the result that I wanted, right? Namely, that the Lebesgue integral of psi, which in the canonical representation is this, I can also express it as this sum, right? So I don't have to worry, as long as these EKs are pairwise disjoint and measurable, I can always write my Lebesgue integral like this. I don't have to make sure that each of these sets is the entire preimage of R, right? Basically, these EKs can be some subset of the entire preimage of AK. All right. So again, this is one of those theorems that it doesn't immediately seem that interesting or cool. It's not a big flashy theorem, but it's a very helpful theorem to have. I'll try to point out from time to time, hey, remember that independence of representation theorem? If we didn't have that, we would have a big problem here. But sometimes even we use it so suddenly, once you have it and you get used to using it, you sometimes don't even think about the fact that you're using it because it becomes so second nature. All right. Now, we'd like to also prove these linearity and monotonicity properties for the Lebesgue integral. So again, these are things that we have for the Riemann integral, and we said, well, we'd really like to have them for the Lebesgue integral. So this theorem states, imagine I have two simple functions, say psi and phi, and they're both zero outside some set of finite measure. Let A and B be constants. Then the Lebesgue integral of A times psi plus B times phi is equal to A times the Lebesgue integral of psi plus B times the Lebesgue integral of phi. So that's the first property. The second property we'd like is we'd like to show, and again, we have this for Riemann integrals too. If f is less than or equal to g, then we like to show that we know the Riemann integral of f will be less than or equal to the Riemann integral of g, if f and g are both Riemann integrable. Here, if we have simple functions, psi and phi, with psi less than or equal to phi almost everywhere, let's remember what that means. That means the property holds, except possibly on a set of measures 0. So if psi is less than or equal to phi almost everywhere, then we would like for the Lebesgue integral of psi to be less than or equal to the Lebesgue integral of phi. All right, so again, we want to spend some time making sure we can prove that for these simple functions. Okay, so to prove the first part, the linearity part, so let's consider the function. So we're considering A psi plus B phi. Okay. So let's take phi's canonical representation to be the sum k equals 1 up to capital N1 of AK times psi of AK. And let's take phi of x. It has its own canonical representation. K equals 1 up to, again, there could be more terms in one than the other. So this is going to be a sum k equals 1 up to N2. And again, this has different values. So let's call these BKs times chi of BK. Okay, so these are the canonical representations of psi and phi. Now, let me define some things. So I'm going to set A0. I can generally assume that all of these are non-zero, the AKs and the BKs, because I'm going to define this function elsewhere, right, to be 0. So let's just call A0 is going to be the preimage of 0 under psi, and capital B0 will be phi inverse, or the preimage of 0 under phi. Then I'm going to form the set. So I'm going to form these EKs. So let me say then set, write it this way. Let's let EK for K equals 1 up to capital N. This is going to be the set of sets of the form AI intersect BJ for all I between 1 and N1, and J being between 1 and N2. Okay, so here's the idea. You have these simple functions, psi and phi, and they're both simple functions, but you can imagine if I were to graph them over here, right? So maybe psi looks like this, but maybe phi, right? Phi, they have a common domain here, but maybe, actually they don't even need to have a common domain. I should be careful here. So like it could look something like this. Now, the problem is when I try to look at this linear combination, the sets on which this linear combination is going to be constant are going to be different than the sets on which psi is constant or the sets on which phi is constant. So what these EKs are doing is they're taking sort of each of these. Now, some of them certainly will be empty, okay? But for example, we have like A1 here, or sorry, this if the pink is phi, so this is B1, and then maybe this set down here is A1, right? Then what I'll get is I'll sort of get, okay, I need to be a little careful here. Sorry, they do actually have to have a common domain, otherwise the sum won't be defined. So let's back this up a bit. I mean, technically I'm defining them to be 0 outside, so it would be okay, but let's just do this for the sake of argument. Yeah. So now my A1 set starts here. Okay. But I get A1 intersect B1, that's going to be my E1. On this little piece right here, A1 plus B1 will be constant. Now, of course, then I have A2, right? A2 starts here and goes over here. Well, A2 intersect B1 is going to be another place where my sum is going to be constant. But then I need to look at A2 intersect B2. So all of these combinations of AI intersect BJ are places where my function will be constant, right? So what it's doing is it's sort of figuring out how we can have some set where these are constant. Now, these EKs are not the sets you would get in the canonical representation. Okay, so we really need that independence theorem here. This is nice. Okay, so if we do this, since the AIs and the BJs are all pairwise disjoint, then the EKs are pairwise disjoint. And further, we can express psi of x not in terms of its canonical representation, but we can express it in terms of these sets EK as AK plus chi of EK. And similarly, we can express phi as a sum k equals 1 up to n of BK chi of EK. Well, in that case, if I look at the A psi of x plus B phi of x, I can then represent that as a sum k equals 1 up to capital N of A times AK plus B times BK times chi of EK of x. And so it follows then from our independence theorem, because again, this is not a canonical representation, but it follows from the theorem then that since I can express this function in this way, that its Lebesgue integral right, has to be equal to this sum, the sum k equals 1 up to capital N of AK plus BK times the measure of the EKs. But now this is a finite sum. We can do some rearrangement to get that this is equal to the sum k equals 1 up to capital N of AK, measure of EK, plus B times the sum k equals 1 up to capital N of BK, measure of EK. So here I'm actually just using the linearity of this sum, but, and maybe to avoid running off the board here, if I look at this, this is the definition of the Lebesgue integral of psi d mu. And this, sorry, I should be careful. This is not the definition. However, by the independence theorem, we previously proved it's equal to this. And this is equal by that independence theorem to the integral of phi d mu. Okay, so we get that the Lebesgue integral of a psi plus b phi is equal to a times the Lebesgue integral of psi plus b times the Lebesgue integral of phi. Okay, so that linearity property does hold. Now, I'm actually not going to spend much time. I'm not going to write out the details of the monotonicity proof. It is in your book, but actually you can sort of cleverly apply this linearity property to prove the monotonicity property. So if you just look at like psi minus, or sorry, if you look at the integral of phi minus psi, you can sort of cleverly prove the monotonicity property using the linearity property. That's sort of the key there. Now, the last thing we want to do is we want to talk about a theorem that somehow starts to relate measurable functions to Lebesgue integrals of simple functions. Now, it will not immediately be clear why this theorem is so important. However, what we will see at the start of the next video is that this is providing us sort of, again, an analogy to how we could think about the integral of, or the Riemann integral of a function as like looking at all step functions that lie below that and looking at their integrals and taking a supremum or infimums of step functions that lie above. We can do something very similar for Lebesgue integrals. But what we're going to be doing here is starting to build some of that theory. So what we want to show, our last theorem we want to prove, is that if we have a bounded real-valued function f on a set E of finite measure, then if I look at the infimum of all simple functions psi that are greater than or equal to f, of the integral over E of psi that has to be equal to the supremum over all simple functions phi less than or equal to f of the integral over E of phi. So again, notice that this is like very close to, right, the condition for Riemann integrability. It's just that we're now replacing we're replacing simple step functions with simple functions and sort of sums here, Riemann sums, or sort of upper and lower Riemann sums with Lebesgue integrals of those simple functions. Okay, so this says this condition holds if and only if f is measurable. So another way, the really most important one is that if f is measurable, then this condition holds. So we want to prove this theorem. Now we're not going to prove every single detail, but I want to focus on sort of part of it to really help you understand what's going on here. In particular, I want to focus on the direction where we suppose f is measurable, and we want to show that this condition holds. Now, similar to a proof we saw in the last theorem, this relies on, so we want to show that f measurable implies sort of this sup equals inf. Okay. Now, the way we're going to sort of go about doing this, right, is we are going to construct a simple function psi that lies above f, but we're actually going to construct a sequence of them that are converging to f, pointwise almost everywhere. And we're going to construct a sequence of functions phi n, each of which lives below f, but is converging pointwise to f, almost everywhere. And then we're going to show that since those are getting close to each other, that the imps and the sups have to be getting close to each other. That's sort of the plan. But we are going to construct these functions in a way that symbolically is going to look strange. I'll try to draw some pictures to help you understand what we're doing. Okay. So suppose f is bounded. And let's give a name to its bound, capital M, and measurable. All right. So for k going from minus n up to n, okay, so for all the integers between minus n and n, including minus n and n, we're going to set ek. Ek is going to be the set of all x such that f of x is between k minus 1 over n times m and is less than or equal to k over n times m. All right. Now, okay, what are we doing here? Okay, so we're really taking our function f. Our function f is measurable, and let's say we know it. It's also bounded. So let's say it's bounded here between m at the top and you know, well, that's fine, and minus m down here at the bottom. Okay. Now, what we're doing is we're basically taking and slicing up minus m to m into, I guess this is like 2n plus 1 pieces. Okay. The idea is we're just going to come in here and we're going to equally partition the range between minus m and m. Okay. So this set ek, what it's doing is, so e sub minus n would actually just give you the things. So if I put in minus n here, the only thing you'd actually get is the places where this is equal to minus m. So the e sub minus n would just be this single point, the single x value where what you get out is minus m. Now, e sub minus m plus 1, now I go up to this interval. Okay. What I look at is I look for all the x values that map into this portion of the range. So then e minus n plus 1 would be like this interval. Okay, and then so on and so on. So you're just looking at, you're sort of partitioning up the range and then looking at, okay, which parts of the domain map into that part of the range. And you're just partitioning it evenly. Okay. All right, now, things to note. The EKs are measurable. Okay, why are they measurable? Well, if you look at this, you can basically write this as an intersection of sets that that come from the measurability conditions. So intersections of measurable sets are measurable. Since F is measurable, this set must be measurable. They are disjoint. Why? Well, it's not possible for two different X values of X there. It's not possible for an X value to map into this range and then another range, right? X values can only map into one of these ranges because of the way I've set up these inequalities, okay? And E is equal to the union of the EK. So remember, E is just the places where the function is defined, right? Okay, so EKs are measurable, disjoint, and E is equal to the union, and I'm just going to write the union over all Ks of the EKs. All right, so you can already see we want to apply the additivity of the Lebesgue measure. Okay, so hence the measure of E is equal to the sum from K equals minus N to N of the measure of the EKs. All right, now I'm going to define some strange looking functions. I'm going to define psi of N. It's going to be the sum K equals minus N to N of Km over N times chi of EK. And I'm going to define phi sub N of X to be the sum K equals minus N to N of K minus 1 M over N chi of EK. All right, what is this doing? What this is doing is it's coming on each of these little intervals, and essentially it's saying, okay, I want to create a simple function that lies below F and a simple function that lies above F. Okay. Well, one way to create a simple function that lies below F is to look at all the X values that mapped, say, into this little interval here, and just round them all down to the bottom of the interval. So there's that. Now I look at all the X values that mapped into this interval, round them all down. Look at all the X values that mapped into this interval, round them all down, right? And I'm not a great artist here, okay? Okay. But essentially you just do this rounding process over and over again. Look at all the things that mapped into this interval, round them down, right? Over here, right, I look at all the things that, I keep doing this. I look at all the things that mapped into this interval, and I basically just round them down. And I just repeat this process over and over. So what I'm doing is I'm basically just taking this and sort of flattening the function down into each little subinterval. On the other hand, so actually that is my phi n. That's what phi n is doing. It's rounding down, right? Because notice that this value that it's taking on each EK is just the lower of the values that defined that EK. Okay. On the other hand, if I round it up, I get a simple function that lied above F. Okay, that's what this does. It's just rounding all the values up. Okay, all right. So that's really what these things are doing here. Okay, notice that by doing this, on each of the EKs, F lies between these two. Okay, so by constructing things in this way, then it must be the case that F lies between phi of n and psi of n. Okay, that's just the way we've constructed these. Okay. And so it then follows that if I look at phi of n minus psi of n, that must, this actually, it has to be greater than or equal to 0. So, what can we say then? Well, give myself some more room here. Keep a little bit of this at the bottom because we'll keep using this. Okay, so what happens then if I look at the infimum over all, of the integrals of psi d mu, and I look at all psi greater than or equal to f, okay, well, certainly that must be less than the integral of these psi n's, right? Because these psi n's, they're particular simple functions that live above f, okay? So I'm taking the infimum over a smaller set, that makes it bigger, okay? But if I look at these, right, because of the way I've defined these psi's, the Lebesgue integral of these will just be the sum k equals minus n to n of km, so the value of the function, times the measure of the set ek. Okay. Similarly, if I look at the supremum over all phi less than or equal to f, integral of e phi d mu, well, certainly that is, that is greater than or equal to the integral over e of any particular one. Okay. And this, by definition, would just be k minus 1 times m over n measure of ek. All right, but now let's just look at the difference, okay? So if I look at so certainly, if I look at the infimum overall simple functions psi, which are greater than or equal to f, so look at the infimum overall psi greater than or equal to f of the integral over e of psi minus the supremum overall phi, simple functions phi less than or equal to f of the integral over e of phi d mu. This certainly has to be positive. All of these lie above all of these, right? And so by monotonicity, they have to, these integrals all have to be greater than these integrals, okay? So the differences here must be greater than or equal to 0. But I've already expressed, or at least have some inequality here. If I replace this with something that's bigger and this with something that's smaller, that just makes the difference bigger. So if I take the difference between these two, okay, that will be bigger than the difference between these two. But the difference between these two can just be expressed as m over n, a sum, k equals minus n to n of m over n mu of ek. Okay. But notice that this is independent of k. Sorry, this should be a little n. This is independent of k, so I can pull it outside of the sum. And recall earlier we showed that this was just the measure of e. This is m over n times the measure of e, and the measure of e is finite. This holds for every n. So taking a limit as n goes to 0, this is going to go to 0. So I have that this difference is bounded below by 0. It's bounded above by something which is going to 0. And so the grand finale then is that this thing has to be 0. So the infimum, and I'm not going to write all these, but basically this thing in the middle here has to be 0. So the inf is equal to the sup, which is what we wanted. Now, for the other direction, we have to do some more work, okay? And the other direction, I think, is actually quite a bit. You can actually prove it fairly short, but I think it's a little less intuitive. I encourage you to go read it. We've already spent quite a bit of time in this video looking at some of these properties, so I don't want to make it much longer. But go take a look at that proof. You can see if you can reason through it. Why is it the case that if the infimums are equal to each other, then the function must be measurable? Of course, as you can imagine, we only have two ways of proving something is measurable. So one is you can just use the definition and show that one of the measurability conditions is satisfied. The other is that by the last theorem, the very last theorem in the previous video, you could alternatively show that there is a sequence of simple functions converging pointwise almost everywhere to that function, right? To that function f, right? Here, I think in the reverse direction, the way you do this is actually to just show a measurability condition is satisfied. There is an alternate way of proving it, though, using that convergent sequence of simple functions, right? So that's another way to get at this. Okay. So we'll conclude this here with these tools in hand. In the next video, we will be able to define the Lebesgue integral of any measurable function.